We'll probably be starting, so welcome everyone to this fifth instance of the seminar series on generative AI and drug discovery. I'm Michael Bronstein. I'm a DeepMind professor of AI at the University of Oxford and also chief scientist of Fund AI, who generously sponsors this series. And today we have another double bill, so it's a great pleasure to welcome Alex Tong and Bose. So Alex got his PhD from Yale University and did a postdoc at Mila, and he's one of the co-founders of a cool startup that does protein design using machine learning methods called dreamfold. And Joy did his PhD at Mila, and he's an incoming postdoc at Oxford and also part of dreamfold. And they will talk today about the fresh from the oven paper on equivariant stochastic flow matching for protein backbone generation. So without further ado, thanks guys for joining, and the floor is yours.
Perfect. Excellent. Okay, yeah, so we're talking about flow matching for protein design today. So the basic problem is that with a lot of caveats, protein structure is what determines function, but it's very hard to figure out exactly which structures are valid folds. So the problem we're looking at is how you generate novel structures without regard to sequence at first, but just how do you design 3D structures that can be folded in real life. And so this is building on some previous work, so especially AlphaFold, which goes from sequence to structure, and using this sort of technology of folding model, but then also diffusion type models that also use AlphaFold ideas to generate structure from Gaussian noise. So there's sort of many different representations of proteins that you can use. We use a particularly popular one, and Joey will tell us about this. But yeah, so that's the basic plan. We're going to do sort of flow matching instead of diffusion for generation. On the side. So yeah, so basic main ideas is that really we want to utilize the priors from protein folding, so from AlphaFold. We also want to use sort of the priors from frame-dip, which is the previous model of diffusion. And then we want to use flow matching, which is, we've shown in previous work, it's sort of faster, more flexible, and easier to implement than diffusion. This is sort of the basic idea. Of course, the challenge is in the details. How do you get these things two things to work together? So that's what we're going to talk about today.
Yeah, so taking over from Alex over here. So the first problem is like, before we can even do flow matching, we have to first understand our data type here and how do we represent protein backbones. So for our talk and for the rest of this talk, the way we'll think about protein backbones is that we'll have a protein which is of length n. So these are n residues, and these n residues have some fixed coordinates. So n, C alpha, C, and oxygen, and they're in Cartesian coordinates, but we will center them at an idealized frame. And the idea is that each residue in our protein backbone is going to be in some sort of rigid transformation away from this frame. So for instance, we'll call this rigid transformation, let's call it x superscript I, and it's composed of a rotation and a translation. And because it's composed of a rotation and a translation, it's part of the group SE3, which is the group of 3D symmetries, including rotation, translation, but not reflection. So R specifically is a rotation, and it's part of the group SO3, which is a group of rotations, and S is a group of 3D translations as well. So given our idealized frame, we can take any protein backbone and basically think of it as an offset from this starred version of the idealized frame. So to get a bit more intuition for exactly how we represent these objects, so if you take one residue and one residue in isolation, and we say it's part of the group SE3. So the first component of the group SE3 is the group of rotations. So the group of rotations is called the special orthogonal group in 3D. And if you're familiar with some of this, this might be very easy to you, but if you're not, it's a good refresher. So the SO3 group is the group of 3x3 rotation matrices. And I'll remind you what a rotation matrix is. A rotation matrix is an orthogonal matrix such that the transpose of itself gives it identity, and it also has determinant 1. And associated with the rotational group is the Lie algebra of the group. So the Lie algebra is a very nice construct because it's actually going to be a vector space. And the special orthogonal group doesn't have this nice structure, but the Lie algebra actually does. So the Lie algebra associated with the group is also if you want to be a bit more formal about it, is the It's the identity element of the group, the tangent space of the identity element, and it's composed of skew symmetric matrices. And I'll remind you what a skew symmetric matrix is. A skew symmetric matrix is any matrix, if you take its transpose, it's the negative of it. So we're going to exploit these facts later on to build our actual flow matching model, but it's good to see exactly what these group elements actually mean. Now, the reason why we're going to talk about all these group elements is that we're going to actually use some group operations. And these group operations will be kind of fundamental to us when we want to kind of go and design our flow, because we'll have to be conscientious about where the exact vector fields are defined. So the two key group operations that we're going to concern ourselves with is the matrix exponential and the matrix logarithms. And for Lie groups, which is the groups that we're concerned with today, which is the group SO3, this matrix exponential corresponds to the exponential map, and correspondingly, the matrix logarithm corresponds to the logarithmic map. And the key idea here is that both of these have a nice power series representation. And the matrix exponential intuitively takes a group element from the Lie algebra and maps it back to the group. And the matrix logarithm has the inverse operation. So finally, the other key object that we kind of need for all of this is to kind of like define a metric. Now, a metric, if you remember from your undergrad math classes, is any bilinear form that satisfies three different axioms. The most important axioms is that it kind of gives you it's symmetric. It also is equal to 0 when the elements are the same. And it also satisfies the triangle inequality. So in our case, a metric is going to be this inner product, which consumes two elements from the Lie algebra of the group SO3, and is going to be defined as the trace of the inner product between the two matrices. So once you have this inner product, you kind of actually have a lot of power in defining many different artifacts. The most important of which is that we can define a distance function on the group SO3. This allows us to compare two different rotation matrices. So very intuitively, if you have two rotation matrices, R1 and R2, the distance between them is going to be essentially the relative rotation between these two matrices, kind of. So if you think of this distance over here, we have the logarithmic map between R1 transpose R2. Now, I'll remind you, R1 transpose, because it's R1 is a rotation matrix, corresponds to the negative rotation. So it's the angle between the two matrices. And because we take the logarithmic map, it's going to be in the tangent space. And finally, we take the Frobenius norm of the two matrices. So this allows us to essentially compare the difference between two rotation matrices. So the main group that we're concerned with is actually SE3, which I mentioned earlier is composed of rotations and translations. So correspondingly, just with SO3, we can extend the same ideas of defining a metric as well as defining the exponential and logarithmic map to the group SE3. So the group SE3 is again composed of rotations R and as well as the translation element over here. And it has a corresponding Lie algebra, which is again composed of this calligraphic math frac R, which is going to be your skew symmetric matrix, and as well as another translation as well. So in boring details, again, we can do the same kind of idea of defining a metric on SC3. And the way we do that is we first choose an inner product. And I should really mention that this choice is free to us. And there's many other possible choices. But this choice over here is actually going to be very useful to us, because if we make this choice of this inner product, we have this very nice decomposition where the inner products decompose into an inner product of SO3 and an inner product of R3. And this is really nice because the inner product in R3 is very familiar to us. And the inner product in SO3, we just defined previously. And using these two kind of ideas, we can define a corresponding distance on SE3, which is going to be the square root of the distance on SO3 plus the distance on R3. So this gives you a really nice way of kind of like reasoning about rigid frames, which are going to be useful for defining our actual protein backbones and how we actually define our flows. And this kind of brings us to like the next part, which is how do we actually do flow matching on Riemannian manifolds?
Yeah, so I'll talk a little bit about this. So Riemannian flow matching, there's also a paper called Riemannian flow matching at Nycler, and our work also builds on this, right? But I think what's special about this work is that we're sort of interested in these SE3 space, and so we're interested in SE3 Riemannian flow matching. Yeah, so a little bit about sort of flow matching in general, but starting from diffusion models. So I think most people understand what diffusion models are here, but the general idea, right, is you add noise and you try and learn a score function to go back from noise to data. So this works very well in images and other spaces, especially when you have Euclidean metric, right? So in this sort of space, the score function is very easy. It's since pt given x is a Gaussian, then it's just xt minus x over some sigma, right? So it's very easy in that space, but it gets much more complicated in Riemannian spaces, right? So that's one of the key things, is that it's not always easy to find a score for sort of the diffusion process in a given space, right? So this diffusion process can have many different forms. And in the case of SE3, there's a very special IGZO density that is hard to take the score of. So it's sort of one of the challenges of diffusion models in this space is calculating the score function. So yeah, in contrast to diffusion models, continuous normalized flows is sort of an ODE version, right? So this has been around for a while, even before diffusion models, but the basic idea is that instead of learning an FE, you learn an ODE that goes from noise to data and correspondingly data to noise by looking at the reverse ODE. So this has no score function in it, right? Because it's just deterministic dynamics. But for a while, it was very hard to learn this because you would need to integrate over time and maximize likelihood. And so this likelihood calculation was very slow and it really didn't scale well to images. And so the sort of thing that allows us to train continuous normalizing flows is going to be this flow matching idea. So just in summary, right? So diffusion used to be very easy to train, but very hard to inference. It was hard to sort of solve this SDE to go backward in time. Like numerically difficult, but it's sort of easier to solve an ODE, but it was harder to train these ODEs, right? So this is sort of the state up until last year, I would say, when flow matching was sort of invented and became popular. And so flow matching is a way to train the continuous normalizing flows like diffusion models. So this is called simulation-free training, in that previous methods needed to, say, take a data point, integrate it to the noise point, and calculate sort of the change of likelihood along it. This is still possible with this model, but it's not the most efficient way to train it. And so instead, what we want to do is define a probability path between the data and a prior, and then understand how to sort of train the flow piece by piece. So just like a diffusion model, you want to pick a place in space and time, and then regress your sort of your vector to the right direction. So that's the basic idea of flow matching. So yeah, you need to define this probability flow, and the key is that it's just sort of the derivative of time of the density. That's the flow that we actually want, this UT. But of course, this UT is very hard for any sort of specific, non-trivial probability mass. So the trick is, how do you learn this UT without knowing it, right? That's the problem. So this means, right, like you say UT generates PT if the flow pushes forward. So if you apply UT, so if you take mass centered at P0, you integrate over time using UT, using an ODE, then you can push it forward to PT. So that's sort of like what we mean by generate. That's sort of the property of what matches a flow to a distribution. And the problem, right, is that there are many flows that can push forward to the same distribution, but it's sort of the choice of this matters. And that's one of the interesting things about flow matching. It allows you to think about what the choices are you can make in choosing which UT you use, even given two densities, so P0 and a P1. So that's one of the things we'll investigate in our work. Yeah, so this would be very nice if we could do, right? So this says basically take a network that depends on time and space, and regress it directly to the flow that we know goes from our P0 to our P1. So that would be awesome, except that it's intractable, right? Because we don't know this UT. And so the trick is that we are going to do something that's equivalent to this without knowing UT. There's a sort of a conditioning step. So what we say is that there's the unconditional path, which is the PT given x, PT of x, and then there's sort of conditional paths of PT of x given z. So this is some z. We haven't yet defined it, but you can think about it as like maybe a pair of data points. That's what we're going to use mostly. But then you can also define a conditional distribution, right? So in the same way that it's sort of easier to do score matching if you do conditional score matching, so like based on sort of a Gaussian centered around every point, a similar idea applies to flow matching. Is you can, if it's easier to find this UT given z, then it's much easier to do flow matching than directly on UT. And so, yeah, that's the basic idea here. So instead of directly regressing to UT of x, we're going to regress to UT of x given z. And it turns out that this is sort of the right thing to do, as long as, it's sort of always true given certain properties of Z. And basically Z can't depend on X, but otherwise it's fine. And so you can choose many sort of different Z's. In previous work, you can choose Z as just sort of a data point on one side. You can choose it as data point on both sides. And there's sort of a way to do it choosing optimal transport paths, which is sort of mini batch optimal transport. But basically any sort of pairing works, and they have different properties and give you different results. And so that's the idea, is that you can do gradients with respect to theta. They're equivalent to gradients with respect to theta on the UT that you don't know. Cool. Yeah, so that just one thing, right? Like this norm is with respect to G. So this is the one difference between regular flow matching in the Euclidean space and flow matching on some sort of Riemannian metric, right? So G is the Riemannian metric on the manifold that we're interested in. So in particular, right, it was why we defined this D on SE3. It's sort of the metric that you might want to use in that space. Cool. Okay, so now we get to fold flow.
Yeah, so now that we kind of have like the basics understandings of flow matching, Riemannian flow matching, and kind of like SE3 as a group, the next part is like, how do we actually do flow matching on SE3 directly and do it exactly specifically for protein backbone generation, right? So so this is kind of like our main thesis of our paper. We have full flow, and there's a family of models that we introduced. The first one is just called full flow Blaze, and essentially the intuitive picture as follows, right? So if you have this kind of homogeneous space for SO3, which is the group of rotations, we can imagine the flow as taking a point, which is the red dot, and transporting it to the blue dot. And the red dot's going to be some uninformative prior, while the blue dot's going to be your actual generated sample, right? And the idea is that you want to construct this black path all the way through until you reach the blue dot. So connecting the red dot to the blue dot. And this is kind of what we're going to do, but we're going to do this for all the backbones at the same time. So this is an idealized example on the sphere, which is a homogeneous space. So our first model is, the first thing we have to do actually is like, how do we define a density over SE3? And now, in our case, because we're working with protein backbones, the density is actually defined on SE3N because there are N residues. And there's actually two problems here. The first problem is that for SE3 by itself, we need to define an invariant density with respect to SE3. And because the SE3 group has rotations and translations, you can't really define a translation invariant measure on on any n-dimensional space. And so what we kind of have to do is first, we have to subtract global translations. And this corresponds to like a projection to an n-1 dimensional space. And in this step one, so we kind of have a density over SE3 n0, where the 0 indicates that it's after you subtract global translation. So now we can define actually an invariant measure in this space. And then after that, we need to define a metric on this space, which allows us to define the actual density. So this is kind of the same metric we kind of talked about earlier in the background section. This is going to be our metric on SE3. And I remind you that this metric was a choice. There's other metrics, but because of this choice, it will enable some nice computational benefits to us. So, so the main part of Riemannian flow matching is that we need to kind of figure out how to define this conditional vector fields. So in our case, for the group SO3, and we'll just focus on SO3 for now because this is the more complicated part. The conditional vector field is UT of RT given Z. Now, RT is going to be some noisy rotation at some time step T, and it's going to lie at the tangent space of SO3. Right? And the reason it lies in the tangent space is because it's going to be a vector field, and the vector field has to be tangent to the manifold. So UT is always going to be on the tangent space, while RT is going to be the rotation at that point. So for our use case, we'll set Z, the conditioner, to be the pair of data points R0 and R1. Now, R0 for us is going to be the actual data point that we have in our data set, while R1 is going to be noise. And the idea is to transport R0 to R1. During training and during generation, we're going to flip this. And for us, the most natural way to define a path, so the black line that connects R0 to R1 is going to be through the geodesic interpolant. And the reason this is the most natural way is because the geodesic on a Riemannian manifold, you can think of it as the shortest path between two different points. And for our group of interest, you can always define a geodesic interpolant using the following form. So we start at the point R1, and we take the logarithmic map at R0. So I remind you, the logarithmic map takes you back to the tangent space at R0. and then we multiply it by a time t, and then we take the exponential map at R0. So the exponential map, again, I remind you, it tells you how far you're going to go if you point in the direction of t times log of R1, and you follow that path for a unit time of 1. So the exponential map transports you back from the tangent space back to the manifold. So this is why it allows us to kind of interpolate different rotation matrices all along the black line. So the black line corresponds to, again, different rotation matrices that transport you from R0 to R1. So now that we have this geodesic interpolate, which is time indexed by t, this is kind of going to be really important for us to define our conditional vector field. So the reason is we can always define a conditional vector field by taking the time derivative of this geodesic interpolant, but we're going to do something even more smart here. And because numerically speaking, or computationally speaking, taking the time derivative to compute a loss function requires 2 backward calls during training, and that might be kind of like expensive for us. So instead, we're going to think about the geometry of the problem a little bit and say, well, how do we get an analytic form for this time derivative to define this conditional vector field? And the way we can think about this is as thinking like, okay, if I'm at RT, which direction do I have to go and how fast do I have to go? So if I'm at RT, I have to go to R0 and I have to go in the time that's kind of left to you, right? So the time that kind of left to you is T. So if I'm at RT, the logarithmic map at RT is going to tell me that I'm going to be at the tangent space, and the speed is going to be determined by kind of this division by T. Now, an analogy to Euclidean spaces, what would this kind of vector field look like? So if I'm going to transport in Euclidean space, the vector field would be x1 minus x0 divided by t. So it tells you the direction you want to go to, which is x1 minus x0, and tells you how fast you need to get there. And this is why the division by t kind of is important over here. So this kind of gives you like an analytic form for this kind of vector field. And the most important thing is that because we're working on this Riemannian manifold, the norm that we have to take is the norm with respect to SO3. So this is kind of where the Riemannian part comes in. So how we define the vector field and what norm we use. And the rest of the objective function is kind of the same. So we sample time between 0 and 1, and this is done in a simulation-free manner. So we can sample any period of time. And we sample 2 data points, R0 and R1, and we compute this conditional vector field, and we regress our network V theta directly to it. So this is kind of be the first part of the full flow, which is the SO3 component. And I'll remind you, because of our metric, we can decouple the SO3 component and the R3 component, which means that we can define separate flows on SO3 and R3 in parallel. And we can learn this using the metric extended to this space. So the key idea over here for full flow base is going to be that this Q of R0, R1, this coupling, is going to be independent. So we can independently sample R0 and R1, and then we can kind of like use this in our loss function directly. So again, the vector field is going to be the time derivative, but we kind of exploited this fact that we can use this closed form of this analytic form, but just looking at the geometry of the problem, which is why this is kind of going to be numerically faster. And I remind you again, in analogies to Euclidean spaces, the vector field would have been xt minus x0 divided by t. Okay.
Yeah, so that's full flow base with an independent coupling between R0 and R1. But the next part is full flow OT. So OT stands for optimal transport. And the idea is that you sort of want more optimal paths. So in previous work in Euclidean spaces, it's been shown that if you choose optimal transport paths, you get sort of some benefits in terms of training and inference, in terms of you sort of get faster training, but also faster inference. And this is for 2 reasons. It's because in Euclidean space, the lines are straighter. You need fewer integration steps. So if you were able to do perfect OT, then the lines are perfectly straight in Euclidean space. So each x0, you would draw a straight line at constant speed to your target x1. But of course, OT is hard. So we use mini batch OT, which is an approximation, but we find it still helps. There's sort of another reason that it's useful is because at given sort of a point in sort of time and space, you can look at the directions that you're regressing to. And so for optimal transport, there's actually only one vector, if you think about it, that goes through that point in space and time. And so it's sort of easy to learn because it's a very deterministic regression. Whereas if you look at, say, a full flow base, for instance, then you have a lot of different directions that you would be regressing against. So depending on which sort of pair you picked, you would get a different direction. And so then it's sort of harder to learn, and there's more stochasticity in the training function, and so it's harder to regress to. So it's sort of like this observed phenomenon where if you train a diffusion model, your loss sort of steadies out at the variance, basically, right? So the lower your variance, the faster it goes to zero, and the easier it is to train overall. So that's why we want to do OT, right? And so this is sort of the motivating. So we want to do OT, but not in Euclidean space, but in Riemannian space. And so this is sort of the challenge, but the idea is to sort of use mini batch couplings, and so compute OT on a small set of examples, and then use those sort of unpermute the pairs, basically, right? So in the previous picture, we had like crossing, right? So this happens a lot when you sample randomly and without considering, which pairs should be closer to each other. But OT says basically you should use the pairs that are closer to each other as much as possible, and so you'll never have crossings, right? So crossings are the stuff that causes variance. So how do we ensure these sort of conditional probability paths are optimal, right? Like that's the real question here. And so we use Riemannian OT for the sort of switching around, right? So this cost function C is the geodesic cost. So we defined this in the beginning, right? But this is sort of the cost in SO3 for this instance, but you could think about it as FE3 also, right? So it depends on which way you want to match, but you sort of want to use the geodesic cost between the 2 points, and that gives you the shortest paths between them, and then you can sort of switch things around to get the optimal pairings and then regress to those. So that's the basic idea here. There's lots of notation here. I don't really think we need all of it, but we're just going to sort of use the put forward from the time 0 to time 1, and that's going to be the sort of the paths that we use instead of the UT that we find in the base version. Yeah, so what do you need to solve Riemannian OT? So you need this sort of interpolant that goes from time 0 to time 1, that pushes the point, sort of pushes the density, but also individual points over time, from time 0 to time 1. You can find the coupling, which is what we need to sort of unpermute these two, and so they're the closest pairs. And then so for SE3N, right, the challenge is, right, for SE3 it's easy to find the geodesic cost, but then SE3N we just use the cost n times, and so this is sort of like using a Euclidean distance on the n individual costs. So that's how we're going to do OT in this space. So this gives us a loss that looks well, basically exactly the same, right? Except for this tiny little difference. Instead of sampling uniformly from P0 and P1, we do a sort of a sampling that is dependent and based on the OT. So this pi represents the OT matrix computed in the previous way. So I think next we'll talk about the final part of flow.
So the final, most exotic model that we have is flow SFM. S stands for Stochastic Flow Matching. And the kind of the idea here is that, well, one of the reasons that we suspect diffusion works so well in high dimension is that this added noise that you use during training actually makes it more robust in high dimensions. So we want to think like, how can we kind of actually exploit this fact and maybe define a stochastic version of flow matching? So this is easier said in pictures. So in pictures, we want to kind of do the same thing as full flow OT, but instead of having a path that goes straight using the geodesic interpolant, we want to kind of take this kind of like the straight path, but add a little bit of noise along the way. And the noise is going to be conditioned on where you are in the path. So the same idea still holds. We start from R0 and you go to R1. And the idea is that you're going to follow this geodesic interpolant, but with some noisy version of it. And then you're going to learn how to like also denoise at the same time. But this idea, as simple as it sounds, presents many mathematical challenges. The first one is this idea is that, well, of course, we want to kind of exploit the fact that diffusion works better in high dimension because of this noise. And it's because diffusion is an SDE. And the reason it's an SDE is because we have this Brownian motion term. But how do we have the corresponding thing for flow matching? So, well, you can think of diffusion in many different ways. And one formulation of diffusion is this idea of using Brownian bridges. So what is a Brownian bridge? So Brownian bridge is any SDE process that's kind of pinned at your starting point and your end point. So it's a bridge in the sense that it guarantees that you're going to start at time 0 at one point, and you're going to end at time 1 at another point. And you're going to have some of this Brownian motion that kind of gets the most peaky or highest variance in the middle of the entire trajectory over here. And in Euclidean space, this is really nice because you can define this Brownian bridge in a very nice form, which is this ST minus S0, where S0 is the starting point, divided by time, plus some gamma t, plus some Wiener process. And the reason this is really nice in Euclidean spaces is that you have simulation-free sampling of this point. So if you want to sample a point st, you can use this conditional distribution, which is just going to be a normal distribution with a specific mean, which is going to be a convex combination of S1 and S0, and some variance scheduling. And because you know this exact closed form, you don't have to simulate the SD of this Brownian bridge to figure out what is the noisy point at time t. Unfortunately, this fact does not hold in Riemannian spaces. And in Riemannian spaces, we can define a corresponding Brownian bridge, which is going to have a similar flavor. So instead of st minus s0, you're going to have log of rt minus r0 divided by t. Same kind of concepts that we kind of exploited, which is going to use the geodesic interpolant again and the time derivative and have this Brownian motion. But this Brownian bridge is not simulation free, which means that, like, unlike the nice properties of Euclidean spaces and also the entire thesis of why we wanted to do flow matching, because it's really fast and computationally efficient, we kind of lose this nice property right away. So how do we kind of get around this problem? Well, as in machine learning, we kind of like try something approximately close to what we want to do and pray, and sometimes it works out for us. And in our case, we do a simulation-free approximation that kind of closely matches what should be the real Brownian bridge, which is the conditional path of RT given R0 and R1. And this is the conditional path on SO3. And we hope that our approximation is going to be good enough, with the key caveat that it's going to be simulation-free. So how do we exactly do this? So to do this, we kind of use this new concept called the isotropic Gaussian on SO3, which is the IGSO density. So the IGSO density is one extension of what a normal distribution might look like on SO3. In fact, it's also very similar to the normal distribution in the sense that it's a maximum entropy distribution on SO3. So it's a very natural analog, and it has a lot of nice properties that you would conventionally find in normal distribution. For instance, it's closed under convolution. And this is kind of the cool fact that kind of helps us exploit the simulation-free nature. So the IGSO density is defined in a similar way. We have some sort of mean parameter, and the mean parameter is going to be this geodesic interpolant, and then we have some concentration parameter, which is similar to this variance. So the intuitive picture I want you to have in your mind is that this geodesic interpolant is going to give you this kind of the straight path that we used to have in full flow OT, which is going to be the mean. And then we're going to add a little bit of Brownian noise along the way. And the Brownian noise is going to be dependent on the position you are along the path. And this is going to correspond to a specific point in time as well. So if we follow this geodesic interpolant, because we have this closed form density, which is given to us by this IGSO, we have this really nice simulation free, because we can simulate this any point in time because we have this analytic form of this IGSO. So we don't have to kind of like simulate an entire trajectory to get a point of RT tilde over here. And given this nice form, we can kind of redefine this loss function that we have for full flow OT. The only thing that changes now is how we sample our noisy point RT. So now instead of RT, we have RT tilde. The tilde corresponds to the fact that this RT is coming from this IGSO distribution, not the regular RT that we got from our conditional path. So everything else remains the same. We still have our OT coupling, which is going to tell us which R0 and R1 to build the geodesic path on. And then along this path, we're going to use this IGSO density to sample RT. And then we're going to plug this into our conditional vector field. So the main thing that changes now is where this RT, where we take the logarithmic map at, which is now going to be at RT tilde. So you don't have to take my word for it. We actually kind of tested the fidelity of this simulation-free approximation. So we ran a couple of different tests over here. The first test was to kind of simulate for different values of gamma, this red path, or so red dotted path, as well as the actual black path. So the black path is the actual simulated SD that corresponds to the Brownian bridge, and the red dotted path is our IGSO approximation. And as you can see, for many different choices of lambda, this approximation seems to be very good and very robust. And this kind of gives us confidence that what we're doing is not some esoteric approximation, but actually kind of really close to what we kind of actually want. And so this enables us to like kind of like think of full flow SFM as a real SD that's going to be simulation free, but takes a flow matching approach rather than a diffusion approach.
Yeah. And so just a reminder, like why we want to do stochastic, right? I think like the current thinking is that stochastic is better in high dimensions. It's more robust. And that you sort of always, right? You always have this thing that points you towards data. So your vector field everywhere points towards data you've seen. And so you sort of, you get, you know, you're pointing in good directions, even if you get off track, right? Conversely, with an ODE, if you get sort of far away from your data, then you have really no guarantees where your vector is going to point, and you may end up somewhere very strange, right? So this is sort of the idea. So even though like maybe this isn't even a perfect approximation, I think it still can help because you sort of have this very high dimensional case. It may not reproduce your sort of distribution exactly. You may not care that much, right? It may produce good proteins anyway. So this is sort of our current thinking, like maybe you want to use it even if it's not perfect, but you know, it seems to work pretty well is sort of our current thing. But of course, I would love to prove that it's perfect if that's possible. We haven't been able to so far, but yeah, that would be great. Cool. So onto sort of results. Yeah, so protein. So protein generative models are very strange. Like, how do you actually evaluate these things? I think nobody's really settled directly on this is the perfect way, right? But one of the key metrics is designability. So it's about how well, once you have a shape, can you think you could make it in a lab and actually have it fold to that structure. So it's basically using refolding. So you take a structure that you generate, you apply this model, so this pre-trained model of protein MPNN, which is a model that takes a structure and gives you a sequence. And so, right, it's trying to sort of solve the problem with inverse folding, in that once you have a folded structure, you want to find a sequence of amino acids that gives you back that structure, right? And so the sort of refolding step is that once you have those sequences that correspond with your structure, you refold all of them with ESM fold. So this is a folding model that now goes from sequence back to structure. So now you have, you started with structure, you went to sequence, now you are back to structure with eight different sequences, and you want to say, well, what is sort of a protein is designable if the best one of those has a good RMSD, so root mean squared deviation, so just is very close to what you generate, right? So it says basically, if your protein structure can be sort of applied with these two models to get a sequence that folds back into the same thing, then it's designable, right? And so this is sort of this is a metric that's used fairly generally across different generative models for this stuff, right? So structure only generative models. It seems to work somewhat in the lab, previous methods, but I think it's not perfect, right? But it's sort of the best metric that we have in computation that says how good are these structures, right? So really, it's about the quality of the structure rather than say matching a distribution or any sort of specific other thing. I want to talk about the sort of.
Yeah, so there's many different metrics that we care about. One of them is diversity, especially for proteins. We care about getting diverse proteins. And the way we calculate diversity is we calculate the pairwise TM score of the designable protein. So first we design a bunch of proteins and we filter them based on this metric of having a root mean score distance of less than 2 angstrom. And then we calculate this pairwise TM score between them. And essentially it's given to you by this exact calculation over here. It doesn't really make too much sense to talk about it more than just to say that having a good TM score often correlates with having more diverse proteins in general.
Yeah, basically the idea of TM score is that it should be independent of length, right? So root mean square deviation is much, much higher as you get long proteins, but TM score is supposedly designed so that the length is taken into account. So that's but it's basically, you can think of it the same idea as RMSD. Yeah, so the sort of third metric that we're going to look at is novelty. So right, these are not traditional sort of generative modeling metrics, but the third thing we want to look at is, well, have I made a protein that is not in the training set? Because, well, I don't really care about making proteins that are already in the training set. I want to make new proteins, and I want a model that can be able to make new proteins. So this is sort of saying, I want to generate a protein, and then I want to say, well, what is the closest thing in the training set? And that tells you basically, is something I designed already in the training set and I don't care about it? So you want a higher fraction of proteins that you haven't seen before. So we measure haven't seen before by looking at sort of the TM score to the training data set. And if it's smaller than 0.5, then we say it's sort of novel, right? We haven't seen it before. So that's sort of 3 metrics that we're going to use. Yeah, so onto the sort of table.
Yeah, so this is our big results table. So essentially, we compared with a bunch of different approaches. The most similar to our approach was this paper that was published in ICML last year, which was called FrameDiff, which did a similar kind of thing, but instead they used the diffusion model. They had various versions of their model, and they even updated their model. There was the frame diff official HTML version, and then their improved version. And then we also have the gold standard, which was RF diffusion and even Genie. And these kinds of models were trained on much larger data sets and have many more parameters, but they still represent a good kind of benchmark to compare against, right? And so the key insights from this table is that we have 3 or 4 models, Base, OT, and SFM. For designability, we found that actually full flow OT does the best for designability, because we assume that the straighter paths and the lower variance optimization actually helps quite a bit. However, the key finding as well is that full flow SFM designs the most novel proteins. And if you care about novelty and for protein design, full flow SFM really seems to matter in terms of like getting robustness through the SDE. And about equally, full flow OT and SFM have about the same amount of diversity. So both of these are very good generative models. They improve significantly over the full flow base model, and more importantly, all 3 of our models are significantly better than the frame diff version, which is the diffusion model, which kind of justifies taking a flow matching approach in the first place.
Yeah, and finally, right, you can see on the very right side the sort of iters per second. So this is training iterations. So one of the things about flow matching, right, is we don't need to calculate the score, is one thing I mentioned before. And it turns out the score of the isotropic Gaussian, so the score in the rotation space, is very annoying to compute. So there's sort of no closed form of even the density. And then you're trying to take a derivative of that, right? And so it's very hard to do this. And so this part is slow. But also we made some other improvements that made the model faster overall. So the sort of ideas here, right? We think OT is the easiest to train. So these are all trained for the same number of steps, 600,000 steps. But we think OT is the easiest to train, but it may not be the best. Like it may be producing a lot of things that are similar potentially, right? We don't know exactly, right? But it doesn't seem like it, but there's sort of, we don't know why it's so much more designable, but it's sort of nice that it is. But yeah, SFM is sort of our most novel protein. So yeah, just looking at the curves here, right? So this says sort of how close you are to training set and how many are designable. So it says, can you design a lot of things far away from the training set, right? So that's the basic idea. And so sort of higher lines on the left is better, right? So this says basically that all the folding model, all the flow matching models seem to be more designable, especially in the very far from training data regime, right? So that's, I think, very important for us. When we want to use this in other applications.
So one of the cool findings of this paper is just like beyond just having a new generative model is that we found that inference matters quite a bit. And one of the tricks that we developed for inference that we found universally helped across all of our models is this idea of inference annealing, which is to say that we'll change the inference procedure by introducing this function I of t, which is going to be some constant c times time. And this is kind of have this really nice important effect where we'll initially speed up inference when we're far away from data and slow it down as we get closer to data. And the reason we kind of thought this was a good idea is that we kind of looked at the rotation flow norm throughout the entire inference trajectory. And if we didn't do this inference annealing trick, we noticed that the rotation norm, which is the blue line over here, kind of explodes near the end of inference. But this inference annealing trick kind of helps make this rotation norm go stable so that near the end of inference, you actually get good proteins that are actually quite designable. So this is the main trick that allowed us to get very highly designable proteins. And I think one of the key findings of this paper that may be universally applicable to any protein generative model, because any generative model that operates over multimodal spaces, which is SO3 and R3, seems to kind of benefit from this inference annealing trick. So yeah, I mean, we also tried this across a variety of different use cases, which is protein generation across different sequence length. And across the board, we found that different inference annealing schedules always seem to help. And the one that kind of helped the most for us was this idea of using 10T. And 10T seemed to have like the biggest bang for buck. And it's something that I think every protein generative model may benefit from going forward.
Yeah. So it's sort of strange in that you speed up rotations at the beginning and slow them down at the end relative to translations, right? So you train this model thinking that it's going to nicely flow in rotation and translation space all at once. In reality, it seems like it's much better to sort of determine what the rotations are very early on, right? Remember, time 1 is noise and time 0 is data. So sort of very early on, right, you have a high scaling the rotations. You change your rotation very, very quickly to sort of the right place, and then you freeze it, and then you move your translation to match that, which is sort of a weird thing to think about, right? It's like you determine how all the amino acids are rotated relative to each other, and then move them to the correct location. So yeah, I don't really understand, why this is the correct thing to do, but it definitely seems to work better than other strategies. So yeah, still investigating, I think, exactly why this is the case, but it seems very useful. So yeah, I think one of the takeaways, right, is like when you're doing multimodal diffusion or flow matching models, we should think carefully about how you balance the spaces, right? It's not like you can just throw any model at it and it'll work. It's because, maybe if you train separate models in both, it would be fine. But since you're training a model that depends on both together, both rotation and translation, and spits them out, the sort of model may have biases on which space it pays attention to. So that's just sort of, maybe thinking on this. Yeah, so this was sort of wrapping up our applications for this part, but moving on to sort of a second smaller experiment. So we were interested in, right, one of the ideas about flow matching is that you can start at any prior distribution. So one of the things we would think would be very interesting is if you could say, take some good guesses about what the protein structure is, and then generate an ensemble of the equilibrium distribution, right? So we sort of want to say, well, knowing one protein structure, right, maybe the crystal structure is useful, but we think that understanding the sort of distribution of structures that a protein can be in is very helpful. So the sort of idea here is, can we use flow matching to start with, say, a pre-folded protein? So take, say, AlphaFold or OmegaFold or any of the known folding models, right? Sort of get a distribution of what we think the protein fold might be, and then use fold flow on top of that to train a distribution from those starting points to sort of the MD trajectory, right? So from an equilibrium distribution of the protein state. So we did it on this BPTI protein. And the idea was, yeah, we want to say, well, does conditioning on these, say, pre-folded things help in training, right? And so it's, and can you generate the equilibrium distribution of structures just based on using this flow matching for matching approach? So yeah, this is the sort of idea of this experiment. Yeah. And so, right, like, yeah, as I was saying, unlike the fusion models, right, the fusion models can't do this. You can use sort of stochastic bridges, right, like the Schrodinger bridges, right? But this is sort of a hard type of fusion models, and flow matching. This full flow is sort of, you could think about the SFM as sort of Schrodinger bridge, but it's not quite that. Anyway, it's one of these ideas that you can sample from a source distribution, so an informative source distribution, right, and get to your target distribution, which we think helps training. It's much easier to say, well, here's sort of good-looking proteins and make it slightly better, rather than take very random noise and make the sort of distribution of proteins. So yeah, that was the basic idea here. And so yeah, we're trying to model this equilibrium distribution. Cool. And so yeah, results. Do you want to?
Yeah, so in terms of results for this experiment, so the best way we could test this result is we computed the Wasserstein 2 distance, full flow random, and frame diff approach. And then we also compared with the random prior AlphaFold and actually the Wasserstein distance at the training set. And we also computed like the W2 distance at the 56th residue and the KL divergence at the 56th residue as well.
Yeah, so the 56th residue is the sort of one with the most variation on this protein, so that's why we're interested in it.
Yeah. So in general, we found that like full flow seemed to achieve very close to the actual training set in terms of the Wasserstein distance, and surprisingly does a lot better than AlphaFold 2, which is something that we weren't expecting, but we were pleasantly surprised with. And this is not just the Wasserstein 2 distance, but it's across the most variable region as well for the 56 residue, both in the Wasserstein distance as well as the KL divergence. And we also kind of did like a plot of this across 3 different settings. So we did full flow random, and frame diff, and you can kind of see exactly where the generated samples are versus compared to their density. We can see that the frame diff model, which is in the last column over here, only seems to hit one of the different modes of this density plot, while full flow, the one plot A, kind of hits 3 different modes already. So it's kind of be able to sample more multimodal distributions more easily. So already this is a significant insight compared to diffusion models. And this is something that I think will really accelerate the use case of these models, especially for protein design.
Yeah. So this is sort of fairly early in the training, right? Like if you train long enough, obviously all of these models can match the distribution. So the distribution here being sort of 3 main modes, right? There's one sort of top right, bottom right, and left. And so while they all can match it eventually, we were interested in, well, is it easier to train and how fast do they train, right? So this is sort of saying if you use an informative prior, you can train faster, right? Which is nice, right? Like I think that's as we expect. Cool. Yeah, so this is just highlighting, yeah, the results are very nice here. Yeah, so okay, so this is pretty much the last experiment. So just wrapping up conclusions, then we'll take some questions. So yeah, just in conclusion, right? Like so we compared sort of flow matching approaches to diffusion-based approaches for this protein design task. These flow matching approaches, you can start from any distribution, which is helpful, especially if you've got a good informative prior, as in the last experiment. We showed they're faster to train. So yeah, it's sort of like, we think it's because you reduce the variance at each point in X sort of time and space. And then they're sort of easier to implement. So the score is very hard to implement in the diffusion models. You don't need to deal with that at all in the flow matching models. You can just take sort of the tangent space of the curve. Right? So you never need to worry about implementing the score of an isotropic Gaussian, which you definitely don't want to do. And so the two findings here were optimal transport and inference annealing especially really improved performance. We also measured some other pieces that we didn't mention here. You can look in the paper, but sort of multiple things can improve performance. But these two especially we found very interesting. And the final thing is the stochasticity, we think improves the proportion of novel proteins that are designable, right? So one of the reasons that we think this might be the case is because, well, even if you're very outside of the data, right? So if you're in the novel space, stochasticity is still valid, basically, right? But you can get very weird things when you do, say, just a flow matching model. And so it helps you be more designable outside of the space.
So the final thing that we want to kind of leave you with is this idea that any generative model is beholden to its samples. So we have a bunch of generated samples of different proteins across different length scales, as well as the corresponding refolded proteins that correspond to the gray ones. And finally, if you want to check out exactly all of the gory details, you can check the paper as well as some code implementations in our GitHub repo. So with that, I think we'll conclude, and we're ready for any questions.
Thanks.
Thank you very much, Alex and Joy. So great talk. So I apologize, guys, that I have my little daughter who's also keen to know more about flow matching. So maybe we'll start. So there are a few questions that are more technical. So Matt is asking whether there is a sequence length restriction for the designability novelty result in slide 40. So the evaluation that you showed.
Slide 40. It's a long more. Yeah, that's a good question. Yeah, so we found that we tested. So this is up to like 300, right? And so we think sort of all the generative models that are not pre-trained have a problem with things much beyond 300. So if you look at the curves, basically, designability goes way down after 300, but we think this is also a function of the RMSD cutoff, right? So RMSD scales with length. So, but if we're using a length RMSD cutoff of 2, then almost nothing is designable after 300. And so, but is that really the right cutoff when you get longer? I'm not exactly sure. So yeah, we're sort of limited to 300 in our experiments, but.
Well, also the other point is that the data set that we trained on doesn't have a lot of large proteins. So this makes it a hard generative modeling problem in the first place. So this is why we chose to cut it off at 300 to have a more robust estimate.
Yeah, exactly. And yeah, so the training set we used was proteins of length less than 512 in the data set, and that turns out to be 22,000-ish proteins by the time we trained. And so I would say 80% of them are less than 300, right? And most of them are around 120-ish, right? Like that's the sort of fraction that you see. And so yeah, I think it's hard to extrapolate these long ones without sort of looking at longer proteins or more complex things. So yeah, we'll see. I think expanding this to longer proteins will be very interesting in the future. But yeah, this model already takes a ton of memory in GPU, right? So longer proteins are very hard. I think we can only fit like 4 or 5, like 512 proteins in A100. So you're sort of stretching the limitations of memory without changing the model drastically too. So that could be a direction for further exploration.
Thank you. And then, well, a few technical questions regarding slide 45. Are the 3 plots there illustrating the single generation, and maybe FrameDiff just predicted a helix? So this is also from Matt.
Yeah, that's very possible. Exactly. I think so. Yeah, this is from a single generation. Yeah, it would be interesting to see if they were different. I suspect that when you look at like where the initial folded structure is, it's also in that mode. So it could be like the easiest one to learn or something, right? So I don't know exactly, but yeah, it seems like all the models are biased towards that one.
So another question, what do you think would be the reason flow matching OT performance a bit worse than RF diffusion? Well, maybe it refers to the last table. I guess I know the answer, but yeah.
Yeah, so I think that's a good question, but I think we put RF diffusion as a comparison, but it's not really the fair comparison because RF diffusion was trained on a significantly larger data set, as well as it's a model that's also about at least 3 times larger, even 4 times larger than full flow model. So although it gets a better designability, we suspect that if we scale full flow to the same size and the same data set, which is hard to acquire, we would achieve better, or if not the same performance.
Yeah, and it's really down to the pre-training, right? So I think the diffusion model training time is actually, somewhat in the ballpark, right? But it's because you've pre-trained unfolding that I think this sort of that type of model is really powerful. So I think the future is sort of using pre-trained models. So if you look at RF diffusion, for instance, if you don't do pre-training, it does much worse. So much worse than even any of these models basically. So this pre-training step is really very crucial to their performance. And I think it's obviously a trick that should be used because these folding models are trained for orders of magnitude longer than the sort of diffusion models right now. So our models trained for 3 days on 4 GPUs, right? Our diffusion is trained for basically a month on 60 GPUs, right? So that's on the pre-training step, right? So it's sort of like you need maybe an order of magnitude more compute. So potentially running these models longer, you might be able to get some performance, but I think that's a big investment to make. Yeah.
So do you think it's possible to retrain your model?
Yeah, so we're definitely interested in this, and we think it's possible. Yes.
Another question, is there any intuition of why stochasticity is robust to high dimensions?
Yeah, that's an excellent question. Yeah, so I was giving some intuition, right? I think it's because basically everywhere you're saying your vector should point back to your data, right? Because the score is the function that says everywhere I should point back to my data, and more towards my data the further away I get, right? So this is sort of a very strong inductive bias. Even at high dimensions, it's very easy to learn functions that are like always pointing back to your data, right? Whereas flows don't have this effect, right? Like it's trying to sort of hit it exactly, and so this is sort of a harder function to hit basically. Whereas the score is very robust, so even if you actually start with an entirely different prior, right, for a score model, you can actually get very close to your data, right? And so this is sort of like a weird property of having the sort of diffusionness, technically for some diffusion models, right, there's no information between your prior and your generated samples, which means that you could technically start with any prior and theoretically get to the right distribution. So it's sort of a very robust way of training, right? But it's sort of you need a lot of steps to get the SDE to work out. So that's the sort of trade-off.
Thank you. And well, I think we are at time, so maybe last question. My curiosity, what can be said about generalization of these models? And would these models be better than the diffusion models from that perspective?
Yeah, that's a great question. I think generalization is really hard to measure in these generative models, right? Like I don't really know how to think about it precisely. I think yeah, we haven't thought too much. I don't know.
Yeah, well, I think we have some insights. The first insight is the novelty metric that we're considering, that how far can you have a designable protein outside of your training? So that gives you some glimpses of generalizability. But the main difficulty here is none of the metrics accurately track what it means to be generalizable, because these are protein-specific metrics, not generative modeling metrics. And even in the space of generative modeling, the metrics are kind of like give you a mixed idea of what it means to be generalizable. But there are some interesting new ideas that are coming that exactly measure generalizability, diversity, and fidelity of samples for generative models. And I think some of those metrics could be applied here, and I think that's what we're actively working on. And hopefully, we will have a more robust answer soon. Yeah.
Thanks, guys, again for joining. So it's really a pleasure having you, and thanks everyone who participated in this talk. So thank you very much, and as usual, it will be published on YouTube for everybody to view afterwards.